Next, let's discuss the impact of data packing and key handling overhead inside the KV SSD. So we want to exploit the parallelism provided by the school SSD architecture of multiple channels, multiple dies, multiple planes, multiple blocks, multiple pages inside each block as much as possible, right? So on the block SSD, when we have IO, when the workload is running, then so many operations are done on the file system side or on the operating system side to arrange this key value pairs into this fixed size blocks. Once we are done with all these operations, then this fixed size blocks are issued to the device. So we know the LBA ID and we know the mapping of how these LBAs are mapped to physical pages on the SSD. So definitely you could think that we could do some smart job in how we distribute this data or the order in which we issue. Let's say if we have pool of LBAs to which IO needs to be happened. So we can schedule these IO requests in a fashion by which we can exploit the parallelism inside SSD at in the best possible way. The scheduling of arranging this request into some particular order in order to take advantage would definitely take some time, but there is benefits of that because once the data is arranged, first we can perform IO in a much quicker way if we do it in parallel and so on and so forth. But now in KV SSDs, because we do not have file system that does all this work of neatly arranging and packing the key value pairs into those fixed size block for us, these key value pairs as it is in its raw form are issued to the device. In the device, as we just saw, we have this indexing structure of request handler, index manager, global index, and this indexing structure needs to be pre-designed by using some fixed mapping logic, such as multi-level hash index, log structured based index, something like that. So when a certain key value pair comes, we exactly know with this logic where this key value pair will be stored and how it will be stored. When a retrieve request for certain key value pair comes, because we have this fixed logic, we can again refer to that logic and find out, okay, if we want to read this key value pair with respect to this key, we would get a certain key hash. And where can we find this key hash inside the device? But with these operations, now you can think that we lose the benefit of being able to arrange or distribute these key value pairs in order to exploit the parallelism inside the device. Because right with the application key itself, somehow it's deterministic where this key would be stored inside the device with whatever the index logic that we are following inside the device. So we do not have that opportunity to schedule the IOs inside the device. Now, this trade-off of different types of operation where we have higher overhead to do the scheduling, but some benefit of scheduling. In key value SSDs, we do not have overhead to do the scheduling because we are just not able to do the scheduling. We don't have the venue to do the scheduling. But again, that means we do not have that overhead to do the scheduling as well, right? Which one of this do you think would work better? Or which one of this has an advantage in one scenario versus a disadvantage in the other? Let's look at the data. So if we pack and unpack more data efficiently with smaller page size and at higher queue depth, where we have So here in this plot, what we are showing x-axis is the, I'm not sure why my tablet is acting strange, increasing the slide by itself, but pardon me for those. I'm just moving back. So on x-axis, we have value size, which is the application workload key value size. And then on y-axis, what I'm showing is the ratio of KV SSD over block SSD read latencies and write latencies. So lower the better. And we have two queue depths, queue depth equal to 1 and queue depth equal to 64, where higher queue depth means higher concurrency. Higher concurrency means application is issuing multiple IOs in parallel at any given time. So when we have such higher queue depths, then in order to do the scheduling for all these IOs that are received in parallel from application, it is a tough job. And just because it's a tough job, it can take more time. And that's one of the reasons if the overhead is higher than the benefit that we rip from this parallelism, then that's not a good idea, right? So in this plots, we see that for higher queue depth, particularly for this darkly hashed region, we are able to observe that the key value SSD is performing better than block SSD. As you see, the ratio of KV SSD over block SSD is lower. There is another factor, which is page size, that is playing a major role in this data that we observe. Because as we observe, if we increase the value size further, that means now the key value pair does not fit into the page. So a single key value pair can range over multiple pages. In that case, we see that the benefit that we initially saw with key value SSD is now lost. This is because now key value SSD has to manage some other, or key value SSDs have some another kind of overhead in order to manage this additional indexing of single key value pairs mapped to multiple pages. So in case of higher concurrency, we observe that the approach of key value SSD could really be good because we do not have any scheduling overhead. So we can handle higher concurrency with much higher efficiency, but with the caveat that the key value pair sizes, on an average, the size of key value pair should be lesser than the page size. And this is a practical enough caveat because the page size inside KV SSD traditionally could be as large as 4 KB. And a key value pair, the chances of key value pair being less than 4 KB is also pretty high. Some another things to discuss about the impact of this data packing. We see that the low intra-request parallelism also degrades the bandwidth, but improves the latency, as we just saw in the earlier plot. Why do we see this degradation of bandwidth? As we see over here, when we compare this key value SSD plot with the block SSD plot, is because with the block SSD, when we have the smart scheduling being done by the file system, then we are able to organize this data and exploit the parallelism inside the device. Exploiting the parallelism inside the SSD means resulting into a higher bandwidth, but the latency of each IO could be still higher because of this additional scheduling overhead that we are adding to each IO. But the benefit we are getting from that is we are able to somehow perform this different IOs on different in parallel inside SSD. And so overall, bandwidth is higher, even though if we see that the latency is higher for block SSDs. But in KV SSDs, Although we are able to get this reduced latencies or improved latency means lower latencies, still we see that the bandwidth that we achieve if we compare the y-axis of these both plots is much lower compared to the bandwidth that we could achieve in block device. So this is because just we are not taking the best advantage of the parallelism provided inside the SSD hardware. If we figure out again how much bandwidth we get would greatly depend on how our workload is. If the workload is of mixed type and it does not even give the block IO stack much opportunity to do smart scheduling, to organize these IOs into a specific pattern, then in that case, probably this difference between bandwidth between block SSD and KV SSD would almost equate to each other. But just to let you know that there is possibility of this big bandwidth difference depending upon workload. The second thing also, as this square marker shows over here, we did observe for KV SSD a sudden drop at certain granularities, and we anticipate that that drop is because of the misalignment of the page boundaries. So if a key value pair fits inside a single page, best. But if it just over exceeds the size of a single page, that means we are maintaining 2 entries for this just a little bit of more data. But if a key value pair fits exactly 2 pages, then it's worth, because we are using the space for that additional indexing overhead that we are incurring. And that's where we have the sawtooth kind of behavior, where if the page boundaries are just exceeded, then the bandwidth drops. But then eventually, because the capacity utilization of that space of multiple pages makes sense, as the key value pair size is almost equivalent to use those multiple pages, so the bandwidth increases and then it drops again. Lastly, I would like to discuss this problem of foreground GC. Now we have already discussed that how garbage collection is important, but garbage collection means additional operation inside SSD, and additional operation means additional time. So not that good. But still, if this garbage collection is done in the background, then doesn't matter much. By what I mean in the background is it doesn't fall in the critical IO path. So if the workload issues a read request, the IO path or the end-to-end latency of that read request doesn't have to include the latency of performing garbage collection. In order to do this read, it just happens irrespective the time that we take in order to perform this reads. It doesn't depend upon how much time the background garbage collection operation is taking, then it's fine. But if we have like update request, and if we do not have sufficient number of free blocks inside the SSD at that time, then what happens? We cannot just write this update into one of the free block and mark the original page invalid, because we just do not have space. Rather, we would have to wait. This update request needs to wait for the garbage collection to complete, and give, as a result of the completion of garbage collection, we would have some more free blocks or free pages inside the blocks. And then we can use this update request to store the data into this free blocks or free pages. So in that case, because now this update request is waiting for the garbage collection to finish, we would call it as foreground GC. Or somehow the time that garbage collection takes to complete, that impacts our IO latency. So having this foreground GC, as you see, is definitely not good. But the chances of having foreground GC in key value SSDs are way higher than the chances of having foreground GC in block SSDs. We observe this from our data. That's because, as we see here, first let's see how do we conclude that the chances of having foreground GC in KVSSD is higher. Here we are showing the normalized bandwidth of running the workload on KVSSD with respect to block. We see that the bandwidth is very high, bandwidth higher the better. The bandwidth remains high while we run RocksDB on a block SSD over ext4. But this bandwidth starts with very high bandwidth, but eventually at some time upon continuous update, we see that the bandwidth drops significantly to a very low level. And then it almost remains the same. So this is the region where foreground GC is happening. So the performance of IO rate is being impacted by the rate at which GC is happening on the device. And similarly, if we do pseudo random update, so 100% random update versus pseudo random update, we see the similar drop and the background or foreground GC phase. Why would this happen? Can you think about the reason? Are you able to connect the dots backward? Why KVSSD is more likely to suffer from foreground GC, as we see over here in the plots, while the block SSD doesn't? The answer is right here on the screen, where if we compare this to sample stack, in the block SSD, while RocksDB is running over block SSD, it's using file systems such as the ext4. So we have this data key value pairs arranged into SS tables in a sorted fashion. And when the file system merges different SS tables into a new SS table, it invalidates these SS tables at once. And invalidation of a whole SS table is high likely to incur an invalidation of all the pages inside the block. So when GC triggers, as we discussed earlier in this lecture, if either whole block is valid, then it is not even a GC candidate. So why to worry? If the whole block is invalid, it's a GC candidate, but it's an easiest GC candidate because you don't have to write anything. So we don't incur any write amplification, internal writes or write amplification. In that case, we can directly go and erase whole block because all the pages inside that is invalid. So when GC is triggered, if we have many blocks that have all the pages inside that as invalid, GC cycle would complete very soon. So even before application, like although if application is issuing this bunch high traffic of key value pairs updates, but still because GC can complete very fast. So at any time we would have more number of blocks with free pages. And these updates could be directed to store into these free pages just by invalidating the previous version of this data. But what happens on a key value SSD, because we do not have any such sorted notion above the key value device, so these key value pairs are directly stored on the key value device using some of the key value device indexing structure. The device that we studied here in this results used the indexing structure of multi-level hash table. And as you know, that multi-level hash table again itself also does not have any sorting notion. So these key value pairs are depending upon the hash function, they are just distributed all across on the SSD into the pages of different blocks. Now, when update come for these key value pairs, usually what we would end up doing is just invalidating previous versions of this data that's spread across everywhere. So the likelihood of invalidating all the pages inside the block is way reduced compared to the sorted arrangement of data in the block device with a file system that sorts it for you. And because of this reduced likelihood of finding that awesome GC candidate, which has all the pages inside that invalid, so you don't have to do any additional work, while GC is triggered, we would end up doing much more additional work for collecting the invalid space from each block. So in this case, we would have to copy these 3 valid pages into a free block, and then we can erase this data. So all that latency to read this valid page, to write that valid page into another free location, and then erasing the data, that consumes some time. And imagine there are many such blocks. So this additional time for each of these blocks, which could end up eventually in a situation where you do not have any free blocks apart from the ones that are already in use for the GC. So the shortage of free blocks would then be translated to asking application to wait, right? Because if a storage device does not have any free block, there is no other option rather than asking application to wait, hold on, I'm generating this free place for you. It's something like you have this guest who appears at your home suddenly, and then you don't have a room ready for them. So it'd be like, wait, can you please sit here in the living room or the dining room for a while until I go up and clear up a room for you so that you can get yourself settled in the room. So that's exactly what's happening here. That's exactly what garbage collection is doing here. And because this IO is supposed to wait, this latency of waiting is translated into that latency of IO. And that results in the decrease in the bandwidth. If many such IOs needs to wait for some or more time, eventually it would reduce the bandwidth of all the IOs. So it would reduce the rate at which all the IOs can be completed. So finally, hurrah, we have reached until the end, right? In the conclusion, we see that major observation of this work on key value SSDs give us the pros, such as key value SSDs may provide lower IO latency, especially when we have concurrent IOs. So it can provide better performance at high concurrency, at higher Q depths. But still, open challenges to resolve in this domain is how do we index? How do we maintain the indexing structure efficiently inside KVSSD? So how do we ensure that the index is not a bottleneck by itself? How do we resolve the challenges such as what we just discussed, the foreground GC? So how do we reduce the susceptibility of key value SSDs to such foreground GC challenges? There might be some new technique that you can think of, some new way of doing garbage collection that can help us to resolve these challenges. And also because there is high space amplification for small key value pairs, which we do not discuss much into this talk, but that's what your discussion post is going to be on. So please write a discussion post on the topic of why do you think there is space amplification inside the KVSSDs if for small key value pairs? So explain your own logic of chances of occurring the space amplification when we have small key value pairs inside KVSSD. And that's it. That concludes our today's lecture. Thank you.